Hello folks, this is Aditya. Today I want to talk about our research on effect of security controls on patching windows, a causal inference-based approach. This is a joint work with Dr. Lamine and Dr. Ann. The motivation of our study was twofold. Basically, in a typical enterprise, the timely patching of software is dependent on multiple factors. The business constraints of downtime, or it can be the security policies and our maturity, or user habits. Similarly, we see that around 15 security controls are installed on a large enterprises, and we wanted to understand, does these security controls affect the patching delays? And also, we wanted to know that if they influence, what is the characteristic? Does also the characteristics of security control influence these patching windows? Based on that, so since this is an observational study, we wanted to know so how this can help the defenders. So the defenders can recalibrate and reassess the risk of a given CVE and reprioritize the patching, as well as they can manage and improve the existing security controls and their investment, and also pivot the security investments in the right direction, depending on the type of investments they already made. So going back to why we wanted to use causal inference as for this study. Typically in a classifier-centric view, we have a set of features or the observations, and we want to model output, we want to predict an output Y. And we assume that the inputs are all in IID format, IID assumption, and also there is no other external influence of both output and the input on both input and output variables. But as we've seen, there are multiple other factors which affect the patching windows. That's why we wanted to go with a causal inference approach. In the causal inference approach, we see that there are co-founding variables which affect not only the output but also the input and the presence of any external treatments, basically the security controls. So in a typical causal inference model, we have three units, three things. One is the unit, other is the treatment, and the third one is the outcomes. Units are the physical objects, or the objects on which which have been treated, which are treated with some type of, they are exposed with some type of treatment, something called, in our case, it's a security control. And the outcomes are like, there are three different types of outcomes: potential, observed, and counterfactual. And when we treat a unit, we need to take care of how the pre-treatment variables or the background or co-founding noise, as well as the post-treatment variables which are affected by the treatment, and the measurements like average treatment effect to individual treatment effect. So from the problem point of view, so if we go back and look at our problem again, so we have an asset which is exposed to a CVE, and we have two security controls, A and B, with the mitigation rates for a CVE 70 and 90%. From the observational studies, we get that there is security control installed, there is CVE exposed on an asset, but and there is a patch which was not applied. But we don't know why it was not applied, and we can't access the reason or mechanism why it was not being applied. So when we map that problem into causal inference, we think that we can say that the change of patching window is the effect, basically the treatment effect of security control on that application to apply the patch on CVE. With this as a background, we can model the two questions into the problem. So the question one, we wanted to understand across the population, is the presence or absence of security control affect the system? So there are, for that, we have the CVE features, a set of features which is extracted from the CVE characteristics. And there's a treatment that is a binary variable which says that the presence or absence of the security control is, and the outcome is like the delay in patching. So that means we are measuring the average treatment effect of T on Y. For second question, we wanted to understand not only the effect of security control, but does the characteristics also affect it? For that, we measure the individual treatment effects. For that, here the treatment will be a function of two things. One is the One is the characteristics of the security control, and the second one is the threat on which we are trying to measure on, the CVE measurement. For that, we need to get a continuous function. We need to design a continuous function to make it fit into the ITE model. So in order to do that, what we do is like we create a scoring function. We propose a scoring function. Typically, the scoring function, typically the effectiveness of any security control is measured in multiple criteria, like the effectiveness, coverage, assurance, cost, impact, and mitigation time are 6 types which we used in our study. So how we measure it, like we collect the data sets which measure these criteria, and we weigh them depending on the input given from the security analyst or a CSO, depending on the type of investment they have made. And we use risk and trade-off graphs to get the influence of these criteria on the CVE, and finally compute the scoring function. Okay, let me give an example here. Let's say we want to measure the impact criteria, which is dependent on prevention, detection, and response of the security control is. From criteria weights point of view, security managers can give, depending on, let's say they have already having persons who take care of the response, they give more weightage to detection in the prevention than of response. From risk and trade-off graphs, we can say that, let's say for a given CVE of 7, the risk is 0.7 and the trade-off is 0.3. Then we can define a truncated distribution method where we can see that the weightages are given is 0.7 and 0.3 for that CVE. Now that we have designed the problem and the scoring function, now the data sets we used are like 3 types of data sets. One is the patch status data set, which is coming from Nessus vulnerability scanner, which we collect an output from 2,000 odd enterprises with varied sizes, and the state of the patch status of around 9,000 CVEs which are specific to Windows operating system. And the patch delays is measured by the release time versus the patch applied time. From in order to measure the effectiveness or the properties of the security control, we have 2 data sets, the file mitigation data sets we collect from 500K hashes and see that how and for past 3 months, and which cover around 3,000 CVE exploits in that file, and see that how a security control can mitigate those exploits. Similarly, MITRE has released attack emulation datasets which cover which emulate the popular APT attacks and give the response of different security controls from protection, detection, response point. We use them for the assessment of properties of the security control. For CVE features, we collect around 269 typical features of age of CVE and exploit availability and other features of CVE, but also the textual features which we scan, the extract from media sources and web forums and page sites of mention of an exploit of the CVE, which gets popularized. And we run a word-to-vec model to create that. Given that the experiments, we use the standard metrics, which are popular in Causal Inference literature, the mean absolute error on average treatment effect and the root-cut precision of estimation of heterogeneous effect. For question 1, we wanted to understand the average treatment effect across the population. We use doubly robust estimator, DRB, which does 2 things, which has like 2 classifiers. One is like which fits the treatment and the response with one classifier, and the linear model to predict the response residuals. And we run it across multiple classifiers and see which one fits well with which gives a stable result. For question 2, we have to find out this was more involved because individual treatment estimation or the data sets are very hard to get, because we only, from the observational study, we understand only that the security control was installed and there was a delay in patching. We don't know like if another control was installed in that organization, how the patching would change. For that, what we employ is we use Gaussian distribution of the properties which we extracted in the previous scoring step to create a semi-synthetic data set, which is extracted from real world observation. And we use these data sets to understand the influence of security function, security scoring, depending on the properties. So for this experiment, we run through 4 different IT algorithms like counterfactual regression and causal effect variation autoencoder and dose response network. And we use dose response network for the downstream components as well. So we see that the critical, high, and medium and low are the different buckets we put the CVEs in, and we see how each security control is delayed depending on the type of the CVE. So the results, we can infer multiple things from this, the results. So basically, we see that there is a delay of 9.45 days across the population because of presence or absence of security control across the organization. The second one was like, and also there is a delay depending on the type of CVE used and the type of security control capability, in a way like 5 to 6 days delay in the presence for a high and critical versus 10 to 12 delay and low and medium type of CVEs. What is the takeaway is like organizations that have, so mostly the organizations which have response-oriented controls installed tend to delay the patching more than the ones which have protection and detection. So they are relying on the personnel to get it. Similarly, overall, the results highlight the importance of security controls in defender risk management. So our related work is spanned across multiple research areas: security control, scoring, risk management, and causal inference. Finally, the feature work is we are mostly, we want to apply, since this is one of the interesting output we got, we want to apply it to multiple other areas of the system. Yeah, that's it. Thanks for listening.